In this video, I'll show you how to start with a custom board bring up for this Xilinx Zynq-based development board that I designed. We'll look at initial power tests, interfacing with JTAG, making sure we can talk to the Zynq system-on-chip processing system and FPGA, then look at how we can program a custom FTDI USB-to-UART and USB-to-JTAG adapter, and finally I'll show you how to configure a UART connection on the Zynq in Vivado and create a simple Hello World application in Vitis. In future videos, we'll examine further board bring up, for example the DDR3 memory and DDR3 memory tests, gigabit Ethernet and more. I'll also be making a hardware design walkthrough video of this board, so make sure to subscribe to the channel that you don't miss out on those videos. Thank you very much to Altium for sponsoring this video. The Tetbred PCBs I designed using Altium Designer, and if you'd like to give Altium Designer a try for yourself, make sure to check out the link in the description below, or go to altium.com/yt/philslab, and you can get yourself an Altium Designer free trial, as well as a 25% off your first license purchase. In a future video, I'll also be making a design walkthrough of this board, looking at how I did the BGA fan out, DDR3 routing, Ethernet, and so on. However, I also have a course that I'm currently working on and will be released within the next few months, and this is actually the course board, and we'll be learning how to design this in this course. If you're interested in this course and would like to register your interest, please make sure to check out the link in the description, linking to a Google Forms document where you can register your interest, and I'll send you an email once the course is ready. Thank you also very much to PCBWay for sponsoring this video. I had these prototype PCBs manufactured and assembled by them using their advanced PCB service. The advanced PCB service is pretty cool. It lets you get boards down to a quantity of one. You can even do HDI boards, so with micro vias, buried and blind vias, down to tiny tracks and spacings, small hole sizes, and loads of cool options such as impedance control, custom stack-ups, and so on. And a lot of these options are also used for the Tetbred, and I'll be going through that in the design walkthrough. The centerpiece of this Tetbred development board is the AMD Xilinx Zynq system-on-chip. I won't be going into too much detail what this system-on-chip is capable of. All I can say, it's rather powerful, a lot more powerful, but also more complicated to interface with than a traditional microcontroller or MCU. Essentially, this Zynq system-on-chip is split into two parts. One is called the processing system, which is basically an APU, so an application processing unit, which can run things such as embedded Linux, but also can run bare metal C code. And then the other half of it is called a PL, or programmable logic, which is essentially an FPGA. And both of these are merged onto a single IC, and thus you can imagine the kind of possibilities you have with this. It's incredibly flexible, powerful, very fast, comes in a variety of different flavors, so to speak, so speed grades, number of cores, FPGA fabric sizes, and so on. I'd highly suggest, before we continue with this video, to follow the link in the description, which is a link to this page, and you can read more about the Xilinx Zynq series system on chips. I think they're pretty cool. We can interface with gigabit Ethernet, USB high-speed on the go. As I said, it can run embedded Linux, but we also have the capabilities of an FPGA. So a very powerful, flexible device. I strongly encourage you to read through this and some of the application notes before you continue. Moving over to looking at the dev board itself, let's see what's on this dev board and what we need to test for us to do a custom board bring up. As you can see on the top side of this board, the centerpiece is the Xilinx Zynq system on chip. The specific IC I chose or flavor is the XC7Z010. So not the most powerful of these Zynq devices, but certainly a very capable device and a great starter product, for example, for something like this, a dev board. The Zynq will require external memory, first of all in the form of DDR memory, and I've decided to include two of these memory ICs you can see on the left-hand side, so two DDR3L low-power memories, and these are routed in a flyby configuration, and more of this will be in the course and an upcoming hardware walkthrough video, but essentially this gives us 1 GB of RAM interfacing with the Xilinx Zynq system on chip. Above, we have this QSPI flash memory, which can be used as a configuration or program storage for the Zynq, so programming the FPGA or the processing system. I've also included some eMMC memory, and this is just for program memory, anything the application might need. Essentially, you can think of this as a fixed SD card for now. Moving further to the right, you can see we have a gigabit Ethernet jack, so an RJ45 jack, as well as this IC right in the center here, which is a gigabit Ethernet physical layer, or PHY for short, and this also interfaces with the processing system of the Xilinx Zynq. So really cool, the Xilinx Zynq has got a hardware MAC which interfaces with the PHY. This enables up to gigabit Ethernet. We move slightly below, the IC and this connector here are USB on the go. On the go meaning the Zynq can present itself as a host, a USB host, or present itself as a USB device, depending on what configuration we want. To do that, we need this IC in the middle, which is USB physical layer. Simply speaking, on the right-hand side, we have USB differential pair. On the left-hand side, we have what's known as a ULPI interface. And that interface is with the Zynq as well. So we have native USB high-speed support, which is very cool. For programming, which will be very important in this video as well for basic board bring up and any development you want to do, of course you need to be able to configure, reprogram this Xilinx system on chip. The main method of doing this is by JTAG. As you might have already spotted on the top right of the board, I have a JTAG header, which exposes the 4 main JTAG signals, as well as power and ground, and that pretty much routes straight to the Xilinx system on chip. What I've decided also to include, however, is this FTDI chip over here, and I'm sure you're familiar with FTDI chips. They're oftentimes found as USB-to-UART converters, so I can plug in a USB cable and it'll convert it to UART TX RX signals. So that's one thing I've done, is hooked up the UART to USB to the Xilinx system on chip. But this specific FTDI chip, the FT2232, is also capable of emulating a JTAG programmer if it's flashed appropriately. In this way, I don't need an additional JTAG connector or adapter. I can simply program this whole board via USB connection, USB to FTDI to the Xilinx system on chip, and in this video I'll also show you how to set that up. As a fallback, of course, I've just added the JTAG signals in case this system doesn't work or fails for some reason. Other than that, on this board we have various power sections. On the bottom side of this board you can see I have various different power rails. I have a power input, which is this DC barrel jack. I have a 3.3 volt, 1.8 volt, 1.0 volt and 1.35 volt regulator. All these regulators supply the various different components of this board. Specifically, the Xilinx system on chip requires about 4 different high current voltage rails for this thing to even boot up. And we'll talk more about this in the course and more about this in upcoming hardware design videos. As you might already be able to tell, comparing this to a microcontroller-based design, this is a lot more involved and a lot more things have to go right for this thing to even boot up. And we'll see that more in this video as well. Just a brief look at the bottom side of this board. Because this is a development board, I've added some extra features in. So for example, I also talked about on the bottom left-hand side, we have this USB connector, which is the debug or USB-to-UART and USB-to-JTAG connector, which goes to the FTDI, which goes to the Zynq for programming. I've also included on some mode select pins on the top right. We can see these mode select pins, and these can switch if we want to boot, for example, from the QSPI flash, from the eMMC, from JTAG and so on. But I also included these mezzanine, so this top connector and this bottom connector, mezzanine or board-to-board connectors, and I've exposed many of the processing system and programmable logic pins, so you could make, for example, your own carrier board if you want to maybe connect this to an audio codec, additional peripherals and so on. These are just essentially expansion slots, so to speak. In any case, now that I've shown you a brief overview of this board, we're ready to start trying to bring this up, connect to it, and see what kind of tests I would do when I first get one of these prototypes into my hands. We'll start off by looking at the relevant voltage rails, making sure the power is there, the voltages are correct. And then we'll check, first of all, the JTAG connection, making sure we can even communicate with the Zynq, make sure it's there on the JTAG line. Then we'll check out the FTDI connection, seeing how we can flash that, so we can have that interface between USB-UART and USB-JTAG. Then we'll move over to Xilinx Vivado, the programming and configuration interface for these Xilinx Zynq modules, and I'll show you how we can configure that and write a simple Hello World application. Let's get started. So here I have one of these ZBread prototype boards ready to be fired up. I've already checked this board's between at least the main voltage rails. If there are any shorts, and there aren't, and this is the first thing I would do first of all before I apply any power, is check for shorts along the voltage rails and just check the board, inspect it manually, maybe under a microscope, to see if everything has been assembled okay, if I can see any obvious defects. I would definitely recommend doing that before plugging any power in. If you've got a lab power supply, I'd recommend hooking that up and slowly ramping it up to see maybe if there's a short you couldn't detect otherwise. If you're happy with that, I have one of these off-the-shelf power supplies. This is a 5 volt up to 2 amp power supply with just a DC barrel jack connector. I'll be plugging that in and then we can check the voltage rails. To check the voltage rails and make sure everything's running, I'll be using my Analog Discovery Pro by Digilant, which is essentially just oscilloscope and function generator, and it connects via USB to my computer. I've now plugged in the power and we have some lights on, which is already a good sign. Specifically this bottom right LED, which is this on LED, and this only turns on if the power sequencing is correct and all the power good signals are on, and this makes sure, okay, at least all the voltage rails seem to have stabilized and hopefully the Zynq should now be discoverable. But let's check all the voltages on the scope, so let's move over to the PC and the USB-based oscilloscope. Let's start then by checking the voltage rails, making sure we have 3.3, 1.8, 1.0 and 1.35 volts. And then we also should check the CMOS oscillators making sure that these are outputting the right frequencies. And this is especially important for the Xilinx Zynq system on chip because we have a CMOS oscillator. In the case of this board, it's 33.3 megahertz connected to the processing system side of the Zynq. If that isn't on, if that isn't running, we won't be able to discover the Zynq processing system through our JTAG chain. So that's important to verify. This is the USB oscilloscope software from Digilent called Waveforms, and let me just check the voltage rail starting with 3.3 volts. I'm just probing at the output capacitors. 3.3, then we have 1.8 volts, which seems to be right here, then 1.0 volts, and 1.35. There we go. Of course, this is a very crude check. You should check for ripple requirements, making sure that your voltage regulators aren't providing a voltage rail that's out of spec for your parts because that could really damage them or reduce their lifespan. The USB oscilloscope here hasn't got a high enough bandwidth to check the 33.33 megahertz oscillator, but I have verified that on the other scope I have here, so we're ready to move on to the actual programming part, looking at JTAG first. Now that we've checked the voltage rails rather crudely and we've looked at the CMOS oscillators and maybe what to do once you first get your boards, it's time to check out the JTAG connection and see if we can even communicate with the Xilinx Zynq system on chip before we move even further. This is of course vendor dependent, but for AMD Xilinx, what we want to use is Vivado. The standard edition of Vivado is free, and this supports several devices, for example the Zynq 7 series device we're using in this video and on this board, and this lets us write HDL, run simulations, configure the device, and you can also get it bundled with what is known as Vitis, and this is an IDE or software development environment specifically for Zynq or for microblaze processors, which are soft-core processors which can run on top of FPGAs. So if you haven't done so, I'd strongly suggest downloading Vivado and Vitis. It's quite a chunky download and quite a large install size, but this lets you play around while you're even doing the hardware design beforehand, and it also lets me do pinouts and things along those lines. So I've used this extensively while designing the board. So even before I started designing the board, I started off checking what's possible in Vivado. In any case, I already have this installed on my PC, and now let's hook up a JTAG probe and then see how we can connect to this. I now started Vivado, and what we want to do is create a new blank project for our design. In later videos, I'll show you how to write board definition and constraint files to make it really tailored towards your custom board, but for now, all we need to do is select the right IC. Go to File, Project, New, and we'll create a new Vivado project. Just click Next. I'll just create a ZBRET board bring up, project name, wherever you want to store it, and we'll just do an RTL project for now. And this is where we have to select the part we're using. If you remember back to the start of the video, it's an XC7Z010, and then we have the package type. I'm using a package CLG400, so 400 pin BGA, and my speed grade is 2, so this is the device I'll select. Then click Next, and all you have to do is click Finish. Vivado will now create a blank project. You can see we're using the Zynq 7000 series with this project part. You can of course change target languages and so on, but for now we're not really too fussed about that. What we want to do is check the JTAG connection first of all. I've now removed power again, and now let's test the basic JTAG connection. First of all, I'll be using this JTAG header rather than the FTDI because that's the most straightforward path to the Zynq system on chip. I've got one of these Digilent HS2 programming adapters, which essentially is an FTDI adapter pre-programmed by Digilent and then plugs via USB into my computer. All I have to do is plug that in, hook up USB to my computer and turn on the power, and then we'll see what to do next. Before testing JTAG as well, we need to make sure that our boot mode settings are correct, and this will depend on how you've designed your hardware. As you saw at the beginning of the video when I showed you the actual board itself, I had 3 dip switches which essentially change these configurations, so boot mode 0, boot mode 1, and boot mode 2. And as I said before, this will let you boot, for example, from an SD card, from NAND flash, or from JTAG, and what type of JTAG mode that is, if it's cascade mode or independent mode. It's very important for our tests to put the JTAG mode into cascade mode, and for this I'm setting all of my dip switches to low, pull to ground so to speak, and later on in hardware design videos I'll show you how this is actually routed up to the FPGA, but for us it's important to make sure our JTAG chain routing is in cascade mode. As you just saw, I'm connecting a Digilent HS2 JTAG to USB converter to my board, and I've now got my board powered up as you saw early on as well. What we need to do in Vivado is look at the bottom left-hand side and go to Open Hardware Manager. We can use this Hardware Manager to just probe, make sure that the USB to JTAG converter is being detected, and then what's being detected on the JTAG chain. The way you do that is rather simple. All we have to do is go to Open Target and Auto Connect This will then create essentially a local server, which is essentially an interface to our debug probe. Nicely enough, what should happen if all goes well is we see our Digilant probe listed at the top here, as well as 2 devices. So this already is a great sign. It indicates at least that the Zynq has powered up seemingly correctly and the JTAG interface is showing something. The reason there are 2 devices is because we have the ARM core, or the 2 ARM cores in this case, in the case of this particular Zynq IC, and this will be listed as one JTAG device. And then we also have the programmable logic part, the FPGA part, so to speak, which is a separate JTAG entity. So this is really cool. We have these 2 connections. We have verified that the JTAG interface works and that at least the power to and the connection to the Zynq seem to be working. And this is the first test I would do. To close the connection, right-click Close Server, and this gets rid of it, because now the next test we'll be doing is trying to read and write memory from the on-chip memory. In the Xilinx Vivado install folder, in my case this is under C Xilinx, if we navigate to the Vivado directory and then go to our version number, then bin, what I'd like to show you is a tool called the Xilinx System Debugger, and I can run that on Windows at least by double-clicking on this .bat file, and this brings up this terminal console. This is quite useful for doing initial debugging and checking what's working, what isn't. There's many different commands available where you can connect to various devices, read and write memory, and so on. So let me just give you a quick demonstration how to use that now. The first thing you want to do is type in the command connect, and that, of course, you have to have your JTAG debug probe connected, should connect to that. This again is like in the hardware manager when we said auto connect to target. And you can see this hasn't thrown an error message and it looks like the hardware server is started. Then to list the targets, as we did in the hardware manager, press targets, click enter, and you should see this come up. In the case of this particular Zynq IC, we have a dual core processor, so we're seeing the application processor unit, so number 4 and number 5 are the individual cores, and this entity XC7Z010 is the programmable logic. Then we would like to connect to one of these cores. Let's say we want to connect to the first ARM Cortex core, so we type in target and then the number that's next to it, so target 4, for example. If there's no error message, we've connected to that specific JTAG entity. We can use the MRD or memory read command to read something from the on-chip memory, or OCM for short. And let's just read a random address, and at that address we get all zeros back. Now let's use the mwrite command, and we'll write to that address, let's just say some random numbers, no errors, and now let's read that again. And you can see we have successfully read and written to that memory address, so at least that seems to be working as well, and is a good initial way to verify that you have connectivity and you can access, for example, various registers. Close to the start of the video, when we talked about the actual hardware that's on this board, I also mentioned that other than the straightforward JTAG connection we have at the top right of the board, we also have this FTDI onboard USB-to-UART and USB-to-JTAG converter, which is this FTDI FT2232H. And on the bottom side of this board, as I showed at the beginning, I have a micro B connector, which I can then use to program the Zynq, rather than having to need this somewhat annoying external JTAG debug probe. The nice thing is, at the time of making this video, for the latest Vivado versions, they've included this program_FTDI utility, which also supports the FT2232H. We can run that in Vivado by typing in exec blank program FTDI, and this will then bring up the help menu, which flags we need to specify, for example, which device we're programming, what serial number, vendor information, and so on. Keep in mind, to be able to do this, hardware-wise, you'll have to follow a certain pin out for the FT2232. They state this in the user guide, and you can check out this development board's link and schematics to make sure you have the same schematics in your own hardware design if you'd like to use this utility. I follow this for my board. This also means you will have to attach an external EEPROM to whatever supported FTDI device you're using. Again, we'll cover this more in the course and more in the hardware design video that will be upcoming. Using this utility then flashes the EEPROM in the FTDI, then we can use the USB-to-UART connection directly on the board to program. For the final part of this first board bring-up video, I'd like to show you how to run a simple Hello World application on the Xilinx Zynq system on chip, now that we've verified the JTAG interface, as well as now that we know how to program the FTDI chip using the Vivado built-in tools. What this Hello World application will do is, as the name suggests, simply print Hello World via the processing system's UART interface connecting to the FTDI chip, outputting as a virtual COM port to the USB connector on the bottom side, which I'll just connect to my computer, and we can use something like PuTTY or HTerm to view the output results. This will let us verify the FTDI connection as well, as well as that we can run and program a simple application on the Xilinx Zynq processing system side of things. To do that, let's go back to Vivado in the project we created. On the left-hand side, I'm going to create a block design. Design name doesn't really matter, just click OK. And what we have to do is then add IPs by using this plus button. I'm going to search for the Zynq processing system, double click to add that, and then we have this Zynq processing system. This is also what I use while doing the hardware design. Again, this will be for a different video and for the course. But if I double click on this, you can see all of the peripherals and units inside one of these Zynqs or this specific Zynq system on chip. We can see we have 2 ARM Cortex A9 cores, we have all these various peripherals and so on, and we can use this IP block to customize our peripherals and which one we want to use. In the next video on setting up this board, I'll also show you how to set up the DDR and also do DDR memory tests. If we go to the processing system PL configuration, I've connected UART1 on my set breadboard, and I'd like to run that at 115/200. What we also have to do is set up the bank voltages by going to peripheral I/O pins. Bank 0 I've set at 3.3 volts, however bank 1 I need to change to 1.8 volts. 1.8 volts because this is where all of the high-speed interfaces will be, such as Ethernet, USB, and so on. All we want to do is enable pins 8 and 9, and this is from my hardware design where I've set UART1 to be, so all I have to do is click on that. Optionally, you can add modem signals if your hardware has that, so flow control signals. But I just have RX and TX, TX pin 8, RX pin 9 of the MIO of the processing system. We jump over to clock configuration. This is where we type in our main CMOS oscillator clock source, and for my board, I've set this at 33.3 recurring, which is the suggested frequency you should have for your hardware designs. Everything else we can leave pretty much as it is. We can see what the CPU frequency will be, DDR frequency. Of course, for the moment, this doesn't really matter too much. Other than that, we can leave pretty much everything else as standard and press OK. So to recap, we've added a Zynq 7 processing system IP block, we set the bank voltages, and we've enabled the one UART we have on our board for the moment. Once we have that in place, Vivado helps us quite nicely. At the top you can see we have designer assistance available. We'll just click on Run Block Automation, leave everything as it is, click OK. Then we need to add a processing system reset, so click the plus, add a processor system reset. What we also want to do is connect the F clock, clock 0, to the XI GPIO clock, and then again click Run Connection Automation this time. Select all automation, click OK. And this is just the most basic structure you could have for the Zynq processing system. We've enabled one of the UARTs, we've added some small IP blocks to configure the very, very basics of the system. Next, what we have to do is actually compile this, so to speak, so a very crude way of saying generate this block design, run the synthesis, run the implementation. And once we have this kind of hardware design in place, we can export this to our IDE, which is Vitis, and then we can actually program this device. So this is the kind of very, very basic design flow for getting to the software development environment. We have to configure our hardware first, generate our hardware files, and then move over to the IDE. Once we have this in place, we go to Sources, Design Sources, right-click on our design, and click Create HDL Wrapper. Let Vivado manage the wrapper and auto-update, click OK. This might take a few seconds to complete, and then we can see we have this Design 1 wrapper at the top left. What we then have to do is generate a bit stream, and by clicking that, it'll automatically run synthesis and implementation as well. So we click on Generate Bit Stream. You can say, okay, we want synthesis and implementation. Click Yes. Leave everything as default. Click OK. This might take a couple minutes to complete, depending on your computer. If you'd like to monitor the progress of what are called design runs, you can go to the bottom panel, click on Design Runs, and you can see Out of Context module runs, as well as the synthesis and implementation runs. After a small amount of time has passed, you can see this window hopefully come up, which is the bitstream generation completed. You can view the implemented design, which is quite interesting. So just click OK. And we can actually see the device allocation or which blocks are used within our Zynq processing system. For us at the moment, this isn't particularly important. What we want to do is export now this generated bitstream, so our hardware configuration, to our software development IDE, which is Vitis. The way we can do that first is export the hardware. So go File, Export, Export Hardware, click Next. I would like to include the bitstream. This will export an XSA file. I might just give this a certain name, just that the UART is enabled, for example. Click Next and click Finish. This will then export the hardware, which we can then use in our IDE. Now that we've exported our hardware with this XSA file, we are ready to launch the Vitis IDE. To do that, we go to the top on Tools, and then at the bottom, Launch Vitis IDE. This will just take a few moments. What we then need to do is import the XSA file by creating a new project. So let's see how we can do that. The top left in the Vitis IDE, click File, New Application Project, click Next, and then we need to create a new platform from a hardware file or XSA file. We click Browse and then navigate to the file we just generated. In my case, I exported that to this folder, and remember we called it Design1 wrapper UART. Open that, click Next, and then we need to give this a project name. I'll just call it ZBRET Hello World _UART, click Next, keep the defaults, click Next again, and here we can select an application template. It could either be an empty C++, empty C application, various other ones, but what we're interested in for the moment is this Hello World application, so select that and click Finish. This application is a bare bones template to use the processing system's UART configured as we did in the IP integrator in Vivado, and that will just print to the virtual COM port, which is on our board via the FTDI chip. On the left-hand side, we can go to the Explorer. The first thing we need to change is the linker script. The linker script we need to change because we haven't enabled or set up the DDR memory yet. By default, as we can see here, the memory regions mapped for the processing system are selecting the DDR. We click on one of these regions, we can change it to either RAM 0 or RAM 1. Let's change all of these to RAM 0. Once you've done that, just save the linker script and open helloworld.c on the left-hand side. You can see it's a very simple program, just prints a couple lines and then ends the program. However, let's modify it slightly because I just wanted to continue print something so we can monitor that on the virtual COM port. To do that, I would also like to include a sleep function that we don't continuously send data, but we wait, for example, half a second before sending data. To do that, we need to include sleep.h, then we can use a micro sleep function. So let me just put an infinite while loop around one of these print statements and then use the uSleep, which is the microsecond sleep function, and just do a half a second delay. And we'll just change the text to ZBRET UART test. Then we simply click on the top left icon, this little hammer, which is the build or compile button. Hopefully that should throw in our errors once it's done. There we go. Then we want to set up our debug configuration. Currently I have my board powered on via the DC jack, and I've connected a programming cable. The way we can do that is if you look at the top toolbar, we can see this little bug icon and we have a little arrow next to it. Go to debug configurations, and we need to create a new single application debug. So double click on that, a GDB server, and the default settings are fine for us now. Once we have our debug configuration set up, we can just simply click the run button with the board powered up and our programming cable attached. And if we look on the bottom right hand side, we can see it'll start the hardware server. It's programming the FPGA, which is a great sign already. We can see the code has now started to run. Then with the USB-to-UART connector attached, or if we're just using the FTDI to do both, that's already part of the system. I then open HTerm or PuTTY or whatever your preferred virtual COM port monitoring program is. I look at which ports I have, and COM25 happens to be my FTDI to UART converter port. Baud rate is 115200 as we specified initially. Then click Connect, and we can see we're getting ZBRET UART test out. That's very cool. So this is great because we've verified the JTAG connection, we've verified we can program this device using the onboard memory, we haven't looked at the DDR part yet, and we've checked that the UART to USB FTDI chip seems to be working. This brings us to the end of this first bring up video. We've covered the very basics from checking for shorts, looking at the power supply rails, making sure the JTAG connections work, how to program maybe the FTDI chip if you're using one of those for USB to UART and USB JTAG, checking that we can read and write to the Zynq, and then also testing the UART connection of the Zynq, looking at how we can set that up in Vivado using a simple IP config, for example, setting the UART, the clocks, and so on. In the next video on board bring up, which will be coming out soon, we'll be looking at how to interface with the DDR3 memory and how to run a memory test. I happen to have really verified this with good results, and I'd like to show you that in a future video, how you can do that on your own custom hardware. Of course, there's much more to test on this board. We haven't tested the QSBI memory, the eMMC memory, gigabit Ethernet, USB high speed. We haven't explored stuff such as running embedded Linux, and there's so much more we need to test with this board to make sure everything functions as it should. But I hope this gave you a good first introduction of how you can start bringing up your own Xilinx Zynq-based hardware, and this is of course a similar procedure for FPGAs and other system on chips. Thank you very much for watching this video. I hope it is helpful, and I hope it encourages you to try your own FPGA or system on chip board bring ups from scratch. In future videos, as I said, we'll be checking out other peripherals, also the DDR memory test, which will be up next. And of course, I'd like to do a hardware design walkthrough because we've looked at more of the bring up side, of course, in this video. But I'd like to show you the schematics, the PCB layout and routing, because I think that's quite interesting as well. If you don't want to miss those upcoming videos, please make sure to subscribe to the channel. If you like the video, please leave a like and a comment if you have any questions. Thank you so much for watching, and I look forward to seeing you in the next video. Bye bye.